Alright guys, so welcome to our channel once again. Today we'll be discussing capacitors in series and in parallel. Capacitors in series and in parallel. So in a practical electronic circuit, capacitors are usually connected in a variety of ways. Normally they will have to be connected with an EMF or a battery cell. So usually we demonstrate the circuit symbol of the capacitor using these two equal lines this way, whereas that of the battery or the EMF will demonstrate it using this, where the longer line is the positive and then the shorter line is the negative. So you have to really understand this difference between the symbol or the circuit symbol of a capacitor and that of a battery cell. So let's quickly consider a capacitor or a connection like this. So if you look at this so well, this is a connection in parallel. So I have the first capacitor here, the second capacitor here, and the third capacitor here. So when you observe this, you will see that all the left hand plates are connected to A, and then all the right hand plates are connected to B. Now you see that the positive charge from the battery is coming down towards this, and then the negative charge from the battery is coming down towards this. Now you realize that the potential difference across the C1, C2, and C3 are all the same. So both C1, C2, and C3 have the same potential difference across them. Now this is because the negative charge is getting across to the negative or the right hand plate. Sorry. So the reason is because the negative charge from here, from this portion, is getting down to all the right hand plates of the three capacitors from this point B, whereas from this left hand side the positive charge is getting across to all three left hand plates from this point A. So remember I told you this connection is a parallel connection. So we have to take note that in a parallel connection the potential difference V will remain the same for all the capacitors here in the parallel connection, whereas the charges will vary as well as the capacitance of the capacitors depending on what the capacitance will be. Alright, so we'll go ahead and see the next example. So over here we see the next capacitor connected in series here. So we have the C1, we have C2, we have C3. Now you notice that the potential difference across here, we have here supplying positive charge to the left hand plate of C1, and then over here we'll have this supplying negative charge to the right hand plate of C3. Now notice that the potential difference across these will vary from C1 to C3, and in the case of the potential difference across the three capacitors will be the sum of the individual potential difference of each capacitor. So V here will be V1 plus V2 plus V3, whereas V here is simply the potential difference here. So the potential difference here is constant, whereas on this side the Q, is simply Q. Over here the Q, which is the charge, is the Q1 plus the Q2 plus the Q3. So the individual charges, the sum of the individual charges makes the total charge here, whereas the potential difference across each of the capacitors remain the same. Whereas over here, the potential difference is the sum of the potential difference over each of the capacitors, that's V1 plus V2 plus V3, whereas the charge remains the same across the three capacitors. Alright, so notice that the equivalent capacitance for each of these, whether for the parallel or for the series, the equivalent capacitance of the capacitor will always be C1 plus C2 plus C3. But then in series, we have this to be 1 over CEQ is 1 over C1 plus 1 over C2 plus 1 over C3. I hope this makes sense. I'll go ahead and write this and then make it clearer. Alright, so for the parallel, the equivalent capacitance will be C1 plus C2 plus C3 all to how many capacitors you have, let's say Cn. So whereas for the potential difference across the parallel capacitor will be the same. Alright, so the charge across the capacitor will be the sum of the individual charges, that Q1 plus Q2 plus Q3 all to the last charge Qn. Alright, so whereas in series we have our equivalent capacitance 1 over CEQ becomes 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4 plus 1 over C5 all to 1 over Cn. That's the last number of the capacitor. So for the potential difference V, it will be the sum of the individual potential difference, that's V1 plus V2 plus V3 plus V4 all to Vn. Alright, so the charge across each capacitor remains the same. Alright, so having taken note of this, we'll go ahead and look at some few examples that will help us understand this even more. So I'll go ahead and write this and then I'll show you some examples on the next slide. Alright, for this question, we have, for a combination of capacitors shown below, calculate the equivalent capacitance of the combination and the charge on the 15 microfarad capacitor. So we want to find the charge here, and then we also want to calculate the equivalent capacitance of the capacitors here. So we'll simply go ahead and then break this diagram down. So the first thing is we are going to combine these and then know the equivalent capacitance of this. And how do we do that? The equivalent capacitance of this should be C, let's say this is C1, and then this is C2, and then this is C3, and then this is C4. So for this, we'll have C1 plus C2. So why is it C1 plus C2? The reason is this: the capacitors here are in parallel, so I'll use C1 plus C2 and not 1 over C1 plus 1 over C2. I can only use 1 over C1 plus 1 over C2 if they are in series. So with this, C1 plus C2, which is 10 plus 20, is 30 microfarad. So this is what I have here. I'll go ahead and illustrate the diagram of this. So at this point, this has combined to be 30 microfarad. So now I can now combine these two, that is the 15 microfarad with the 30 microfarad. So let's see, remember this is C3 and then this is C4. So let's say this combination gives us C5. So with this now I have C3 and then C4, but this is in series. So the equivalent capacitance here will be 1 over C3 plus 1 over C4. So what's C3? So I have 1 over C will be 1 over C3 plus 1 over C4. So 1 over C3 is 1 over 15, right? Plus 1 over C. So at this point, I can have 1 over C, or let's say 1 over C6, which will be the capacitance to get when I add this up. So 1 over C6 will now be 1 over C3 plus 1 over C5, which is this plus this. Whereas the first one, we got C5 by adding C1 to C2 here. So we'll get our C6, which is the combination of these, by adding 1 over C5 and then together with 1 over C3. So 1 over C6 is equal to 1 over C3 plus 1 over C5. So what's 1 over C3? 1 over C3 is 1 over 15, right? And then 1 over C5 is 1 over 30. So 1 over C6 is simply 1 over 15 plus 1 over 30. So let's check this up with our calculator. We should have, so with this we have 1 over C6 is equal to 1 over is equal to 10 microfarads. Alright, so since a combination of these gives us 10 microfarads, we'll have a diagram like this. Let's show you. So let me go ahead and wipe this part for space. Here I have 25 microfarads and then I have 10 microfarads. So let's recall that our C3 plus C5 gives us C6, and then over here is still our C4. So we can get our C7, which is the final capacitance, by adding C4 and C6. So what connection is this? This is parallel. So we'll go ahead and then calculate this by saying that C7 is equal to C4 plus C6. Alright, at this point, C7 is C4, which is 25 microfarad, plus 6 is, which is 10 microfarad, and then this is equal to 25 plus 10 is 35 microfarad. So C7 is equal to 35 microfarad. So our alternate connection, or our equivalent capacitance, is 35 microfarad. So this is what we'll have. a 35 microfarad capacitor connected connected with a 60 volts potential difference or EMF of the cell. Alright, so I'll go ahead and wipe this, and then let's check out what will be the charge on the 15 microfarad capacitor. Alright, so for us to get the charge on the 15 microfarad capacitor, we have to understand the connections first. Alright, so if we should go back to the diagram again, so we're back to this point. So we already combined the C1 and C2 to give us C5. So here is the C5, and remember here is the C3, and here is the C4. So now if we want to find the equivalent the charge on the C3 here, which is the 15 microfarad capacitor, we want to find the charge here. Now first of all, we need to realize that a combination of this and this give us C6, right? And then with that we have a parallel combination which gave us C7, which is the equivalent capacitance of the capacitors here. Alright, so if we check out this in the right sense, the equivalent capacitance was realized to be 35 microfarad. Alright, so if the equivalent capacitance is 35 microfarad, and then we combine C6 plus C4 to have 35 microfarad. Now recall that the connection was in parallel, so that shows that the potential difference across that is the same, and our potential difference from the circuit connection we saw earlier on is 60 volts. So it means that actually, remember that Q is CV. Alright, so the equivalent charge here is C times V, right? So it means that C4 plus C6 give us this. Alright, so since this is okay, let me just quickly sketch how the diagram will look like. I'll eventually have something like this. This is C4, this is C6. So C6 will be a combination of these two capacitors, which give us 10 microfarad, and then C4 is 25 microfarad. So since this is a parallel connection, the capacitance here will be 10 plus 25, which is 35 microfarad. That's 35 times 10 to the power of minus 6 farad times V, which is the potential difference. Now also recall that the potential difference across this will be the same since it is a parallel connection. So that is 60 volts. 60 volts. So the equivalent charge here will be this times 60, and then this will ultimately give us 2.1 times 10 to the power of minus 3 coulombs. Alright, so next ahead we'll go, since remember we are trying to move backwards to get down back to this. So now since we have uncoiled this, the next thing is to check the charge here. Now since the potential difference here is the same as that here, so and then the equivalent charge here gives us 2.1 times 10 to the power of minus 3. Alright, now to actually check that of C6 here, so for C6 we'll have the same potential difference as C4, and then this will be now what's C6 again? 10 microfarads, right? So 10 microfarads, which is 10 times 10 to the power of minus 6, and then times 60 volts. So if we calculate this, we'll have 0.6 times 10 to the power of minus 3 coulombs. Now, since this is the charge on C6, now let's notice this. At this point, we want to find the charges here for C3 and C5. Now, notice that at this point, the charge in C3 and that in C5 will be the same, but the potential difference between them will not be the same. So we won't go ahead and solve for this. Already we have the charge in C6 to be 0.6 times 10 to the power of minus 3. If the charge in C6 is 0.6 times 10 to the power of minus 3, it means the charge in C3 is the same thing, and then this charge in C5 is the same thing. So C3 is equal to C5, and this is 0.6 times 10 to the power of minus 3. Now the reason is this is in series connection to this. So I'll go ahead and wipe this, and then we'll consider the next example. So for this next example, we want to consider the charge on each capacitor shown in this figure. Now, for us to consider the charge, this is just very simple for us to do. All we have to do is, this is in series, so the equivalent capacitance will be 1 over C1 plus 1 over C2 plus 1 over C3. Alright, so if we make this 1 over 3 plus 1 over 12 plus 1 over 4 microfarads, we should have our 1 over CEQ to be 2 over 3. So ultimately, CEQ will now be 3 over 2, which is 1.5 microfarads. Alright, so now that we have the equivalent capacitance, we can go ahead and find the charge across this. So Q will be CV, where C is 1.5 microfarad. So 1.5 times 10 to the power of minus 6 times the voltage, which is 16. So this gives us our Q. So 1.5 times this, our Q will now become 24 microcoulombs. Alright, so in order for us to get the potential difference across each capacitor, now let's note that the potential difference across each capacitor will vary. Now this is because these capacitors are connected in series, so the potential difference across each capacitor will vary. So I'll go ahead and wipe this. So let's calculate the individual potential difference across each capacitor. Alright, so now for the first capacitor, which is 3 microfarad, we have our V1, which is the potential difference across the first capacitor C1 will now be the charge over the C1. Now, let's recall that we have our charge to be 24 microcoulombs. That's 24 times 10 to the power of 6. Whereas we have our capacitor here to be 3. The capacitance of the capacitor is 3 microfarad. That's 3 times 10 to the power of minus 6 farad. Alright, so when we calculate this, we have 8 volts. Alright, for V2, we'll have our Q over our C2. So remember, the charge across each of the capacitors will remain the same. That is 24 microcoulomb. So over 12 microfarads. And this will equal to 2 volts. So lastly, we have V3 to be equal to Q over C3. And that's 24 times 10 to the power of minus 6 over the capacitance here, which is 10 to the power of minus 6. Alright, so if we calculate this, we should have 6 volts. Alright guys, we've come to the end of the class for today. If you enjoyed our video, please give it a thumbs up. Also ensure to share to your friends, subscribe if you've not subscribed yet, and drop your comments on the comment section below. See you next time.